I am a CLA. Been a CLA since 2013. Certified now through 2025, I think. I just got my recert. So, yay, the recert by points. If you are certified, I highly suggest doing all of the things so that you can recert by points. I've talked to people who had to take the recert exams, and I've also heard that it's better to just take the exam, the original exam, again than take the recert exam. Anyway, preferences of people that I've talked to. And of course, computers taking forever. It is not a fast computer. It's just, upload first. No, you always fail if I try and recover. Anyone else have that type of problem? If you hit recover here, it just crashes on you immediately. Yeah. So, everyone learning things about object-oriented today? Retaining any of it? I'm going to try not to assume that people have retained everything. I'll try and cover anything that's super important. But had my computer up and running and it decided that it overheated and wanted to blue screen. So this is what we get for trusting technology. So some of the main principles of object-oriented we've gone over today. Abstraction, being able to say, this is a thing, I don't care how you implement it, but this is a thing and you can use it. That's one of the things that we're going to talk about a lot today. Encapsulation, only the class can talk to this data, and nothing else can except through the methods that you give it to talk to the data. Hey, I have a presentation. It's, and you can tell how good I am at PowerPoint by this slide here. Stolen from another one. All right. Yeah, design patterns. We're talking about object-oriented today, and yeah, it's great. Let's make objects. But has anyone done this before? Of course we have. It's been a decade and a half since this came on the scene big time. So people have solved this. We've created wheels. Let's use those. Think I have talked about all of those. Encapsulation, only the class can access data. Dynamic dispatch, also a huge and major part of a lot of what we're going to be talking about today, and a major part of objects and classes in general. Being able to say, hey, I'm this object, but I inherit from this other class. I'm traveling on that class's line. You have functions that this class can do. I can do those too. So I'm just going to do my version of that function. Or if I haven't overridden it, I'll do my parent's version of it. That type of thing. So yeah, with inheritance, you define for the parent the broad or no capability version. Then for children, you define more specific. For future children, you define even more specific until we do something then profit? I don't know. Something like that. These are the design patterns I wanted to touch on today. Singleton pattern. So we have something, usually a communication bus, that only one thing can talk to at a time. And we want to represent that in code. But that means we have to hold it only one copy of that in memory at a time. And so singleton pattern helps us to do that. The aggregation pattern. I have some broad thing that I let you interface with, but behind the scenes I'm working with other things, like a car. You you have your engine, you have your exhaust system, you have your drivetrain. The driver doesn't care about any of that. We want to push the gas pedal, go, push the brake, stop, turn the wheel, go in the correct direction. We don't care about all of the underlying stuff. Just give me a car. Don't give me the engine, have me, rotate specific RPMs. That's not my job, it's the car's job. That's an aggregator pattern. And we'll get into other examples of that later. Factory pattern, we have a generic thing, and we have lots of things that can do this thing, and maybe we farm out to someone else, hey, build things that are like this thing that I can use in this way, and then launch them at runtime, and we'll deal with it then. And then the reason I'm doing all of this, and if you take anything away from today, I want it to be hardware abstraction layers. If you are interfacing with hardware on a project that is going to last longer than a couple months, use the hardware abstraction layer, please. I was working with an engine for years that only a few of its hardware objects were abstract, and as I was leaving that company, the hardware was going obsolete. It may have been the impetus, I don't know. So some of the ways that we approach problems in non-object oriented fashion. Use a gigantic clustersaurus. Put all of our data that we ever need in there. And then, we store that single copy of the cluster. And then when we need it, we pop it out of, Q or wherever we're holding it. And what do we do with it? We unbundle what we need and put that into the function. That interface can be really difficult, especially if you're working with 20 or 30 elements from that cluster. Do you then create a new subcluster that meets all of those things and mates it and brings it in and out? Or do you just pipe the whole cluster in and let me tell you that will eat your RAM faster than anything? LabVIEW, because any subfunction could potentially change your data, LabVIEW will copy it in memory, and that copy is time intensive. So I highly suggest that you don't pump your clustersaurus into all of your subfunctions. Don't do that. We'll talk about how classes take care of a lot of that in a bit. So say we have something like a piece of hardware that at build time we know exactly what it's going to be. And we just have case structures for all of the different versions of this hardware that we could potentially use. And we have an enum going to all of those case structures saying, hey, this is what we're using, go ahead and run this case of the case structure, and everything's fine. Until we go and add another piece of hardware. Now we gotta touch every single one of those case structures. What if we miss one? Everyone's gonna miss one. That's never a fun debug session. Dynamically launching VIs. Very, very useful tool. Love doing it. Getting data to that VI and agreeing on what your interface must be to get the data that you need into that sub-VI, and then out of that sub-VI, and then now we have to store that data. It can be a bit intensive. Classes help us deal with a lot of this, the errors that come up with this as well. So again, back to the singleton pattern. Now we're going to go a little bit deeper into each of the design patterns I talked about a couple slides ago. Ooh, this one right here. So singleton pattern. Again, it's usually a single point accessible something. Hardware, communication bus, something that only physically exists in one point in time, or one location, and we want to represent that thing and have multiple different pieces of code talking to it but not step on each other's feet. Let's look at this example. If my LabVIEW came up, it may have done. No. Okay, here we go. Thankfully, it's not a large project, so it should be downloading relatively quickly. Hey, look, there it is. Go to this singleton pattern and run it. So I have, let's go to the block diagram first. There we go. So here is my UIQ, and I have these two loops down here that each have a version of the class, and this could be dynamically launched, this could be the parent class, and each of them over here was probably performing some action on the class that is atomic. Once it is done, it will release this. But as an example, I wanted to have full control over who has what where. So we go in and have the top loop obtain the item. Notice over here, it has the data now. So if I go to the bottom loop and say, get me that data, it says your data is in another function. Okay. How about if I release 2? That should, overwrite the queue and put something in it, and oh. By the way, that's a bad thing to do. You don't want to do that because the data it would overwrite with would be empty, and you have just lost your actual piece of data and caused many different problems in your function. So note that there is a Boolean in here saying, hey, do I have the data or not? You do want to make sure you track where your data is and who has it if you're going to have it through multiple states like this. So let's have one release it. It no longer controls it. Then object 2 can come over and get it and play around with it and do the things, and 1 comes back. Hey, your data is elsewhere. All right, it's going to stall again until 2 releases, and now we can get it. So that's singleton. Only one thing can have it at the time. I'm sorry, I didn't actually put data in and show you, hey, the data is actually located here. This code is going to be available. You can play around with that as you want. There exists in this data structure actual data that can be written. So upper bound, lower bound measurement, an array of data to write, can be huge. And one of the things with this class line, since you're only going to have the single line, you're never going to branch this because it's singleton. And if you really want to enforce that, have it a data value reference so that it absolutely is one location in memory. Since you're never going to split this, typing it into a subfunction, it'll bring all of your data in, but it won't copy it. And now we can unbundle in that class any single element that we want, and that is not a huge memory hit at all, or any subset of elements because it's all class data. So that's a few of the benefits that a singleton in a class structure is going to give you over just having a huge data cluster. Any questions on that one before I move on? No? Okay. Back to the slides. What do we learn there? Tracking what loop has the object is important. If we lose track of it, we could overwrite with bad data or just lose our data entirely. So make sure you keep track of where your data is. But we no longer have to worry about function inputs. Since everything is part of the class that's going to be acting on this data, it's all going to have the dynamic dispatch enabled for this class data, and through accessors from private data or however you're getting to your data for that class, it should be available on that line. And you're never going to branch this line because it's a singleton. Or if you do, make it EDR. Everyone here know about data value references at least? Yeah, I see nods, okay. Anyone not know about them? Okay, so everyone know about pointers in other languages? Yeah. Data value references are essentially LabVIEW's version of pointers. And if you do a control space data value reference, you'll get all of the palette info for creating, managing, destroying them. So, aggregation pattern. This is an object which contains a bunch of other objects. Usually, since we're test and measurement, test automation, what we're concerned with for the overarching object is our tester. Our tester has all of the different test items, all of the instruments that we're talking to, all of the inputs and outputs, and we should just be able to, in our code, say, tester, set this output to this voltage or current output or whatever, or tester, read this input. And it should be as simple as that. And an aggregator would then go to your tester and say, all right, so here is the output that we want to set. Here's the value that we want to set it. How do I do that? And do all of that interpretation inside of the aggregator, talking to all of your instruments, which it holds control of, to make them do all of the things that the tester is capable of. So it's a way of abstracting out your test machine. There are other things that an aggregator can be useful for. I didn't write them down, I can't think of them off the top of my head. So if anyone has examples. No? Okay. Let's look at the code for this. And this is a really minor example because it is a class which holds a bunch of other classes. And we can, this will come up later, send in an array of instruments and cast them to the specific instruments we want them to be. And now we have a way to say, hey, these are the actual instruments I want you to hold in each of these things. And now we have our DMMs, we have our power supply, we have our digitizer, and we have XY table. I don't know, I just picked a few different things that we might use. And we can talk to those as if they are that thing, but in the context of, I am this test machine, or this test bench, or however you define your tester. So, callers of the aggregation, or aggregating class don't need to know the inner workings of that class. It's one of the good things about an aggregator. The inner classes help to keep functionality apparent to the designer of the aggregator. So the designer of the test bench knows what those things do, but it helps keep it transparent to the designer of your architecture for your test system or your actuation script or whatever you're using this tester object in. Factory pattern. This allows you to have a template for input and output of generic things. Usually this is used in plugins, allowing plugins to be added to your system from third-party sources. It will launch the children of a template, your template class, at runtime, and you don't have to know what that child will be. And sometimes really helpful to say, here is the way that you program this, here's your parent, here's your inputs and outputs and the classes you get, or the functions you have to override. Go, play, have fun. and then people do crazy things like, you know, the internet. I don't know. But a couple of years ago, I did a presentation for the slug community and made a sequencer engine. And it is actually a really good example of the factory pattern. There are actually two in this sequencer engine. The first one is in the sequence reader, because I don't know what type of sequence you're passing me. Is it a text file? Is it an XML file? CSV? Something that you created on your own? Create your own sequence reader, something that interprets that file to your sequence. And here I just have this path hardwired in, but you would do a search on the extension of this via text or whatever, and make a decision off of that, usually. Here I know that it's only XML because I've only implemented an XML reader. In this, we have this one. No. That's reading the XML file. Now, it will be this one. Yes. Yes. So, here, I take a list of actions, and I have some defined here in my actions folder. So, since most systems can do sound, I decided, let's just do something based off of the audio playing capabilities of systems. So I got place stored notes, set tempo, set time signature, and tone. So stuff that you would want when creating something musical. Don't care which one comes in at runtime. I'll just go and get that class and fill out all of the inputs based off of this array. And launch a brand new class of the type in the action to be performed folder name, and cast it to the type action. And now I get an array of actions out, and they're just a bunch of different children. I don't know what they are. So I created for today a sequence. I'm going to briefly show it to you. It is rather simple. It's just a bunch of tone, 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 wait, tone, tone. And we're going to run that in just a second. Hopefully the HDMI sound works. And we shall have a whimsical thing that happens. And here it's searching for what type of sequence type it is. It doesn't know, so it's loading it in a runtime. Here it's looking for CSV. I'm going to ignore that because it doesn't exist. Cell. Ignore text. And it's looking for the weight class. It didn't see the weight class, so it popped that up. Let's leave this running and run over here. Hey, there's a weight folder right here. Maybe if we drop that in our actions folder, it'll do something interesting. And again, it's looking for the types of sequence readers. And it takes a little bit longer because I ignored them the first time. Okay, I'm going to need to unplug this for the whimsicalness. But you did notice. You did notice that it did not stop when it didn't find the weight, because it found the weight at runtime. I just changed the folder structure, and hey, all of a sudden we have new functionality. You know, it's not doing the song. Anyway, believe me when I say it was playing Shave and Haircut. Things we do. All right. So that is the power of not dynamic dispatch, though it is power of dynamic dispatch as well. It is the factory pattern at work. We go out and search the disk and find whatever we find, and we can use it, and if it runs, then good. If it doesn't run, that's another thing. That will throw errors at runtime, and you'll need to handle those well. But this adds a huge amount of power, because now someone can be working on the full functionality of whatever you're working on and say, hey, I know that down the line we're going to have a bunch of these types of things that we can do, and I'm going to tell other people how to do that, but I'm just going to pretend like they work and write my code like they work. And then down the line, when these are done, they can hand them to me, I'll throw them in and it'll work. Because they tested their stuff and I tested my stuff separately, and they just work together. Apparently Steam wants me to log in. As I said, not my work computer. So, one of the big things about factory patterns is they allow plugins. They enable scripting and sequencing. There was supposed to have been a sequencing lecture later today. Sadly, they weren't able to make it. But believe you me when I say this is one of the major ways to do sequencing. And I'm getting there to my most important part. They define what types of hardware instruments we want to run, specific concrete instruments, at runtime, which is a way that we do hardware, oh my goodness, my brain. Abstraction layer. I can remember the word abstraction. So, what is a hardware abstraction layer? Again, most of us are in test automation, test measurement. We have instruments that we're talking to. We have hardware that we're talking to. One power supply almost always, except for in fringe cases, can be replaced by another power supply that does equally well. One oscope can be replaced by another oscope or digitizer or whatever instrument fills that niche. One DMM can be replaced by another. I'm sorry, Fluke. Don't know if anyone from Fluke is here, but I might poke fun at you. But yeah, what happens if a power supply goes obsolete? What happens if the people making these DMMs go out of business and we can't get them anymore? What happens if the drivers aren't supported in 10 years or next year? Adding this layer of abstraction, saying, hey, I want to use this type of instrument instead of I want to use this instrument, allows for great leverage and great longevity of a program. Helps keep us future-proof. I've gone over most of this. So yes, after we have made the abstract versions of the classes, we do need to define the concrete versions of classes to talk to the thing that we actually want to talk to. But changing that out is super simple. So let's take a look at that. Over here in my health folder, I have a config file, and it has all of the instruments I'm using. So the top one is the digitizer, and it's my newest hardware. I don't know what that's going to be. I just threw it in and I noticed. DMM1 is going to be a fluke. DMM2 is going to be another fluke. Our power supply is like a Keyance or something like that. And we made our own XY table, but it behaves like an XY table. So we're going to build the drivers for that and build the interface to that. And those are going to be our hardware instruments today. How do we get that into our code? When we launch our code during our initialization feature, and I didn't get anywhere past the initialization because that's the important part here. We go to our handy-dandy config file reader and read all of the different objects that we want to run right now, this very instant when we start. And yeah, this can be as an initialization that you call from a menu or something else. But it's when you initialize your system and you know what you're using. You go to your config file, it reads everything in and says, all right, I'm going to define my hardware as this. And this is just names. Usually going to be folder names or class names, so that when we go to, when we go to our, hey look, it's a factory pattern. We just talked about this one. We can go to our location of all of our hardware classes. I don't know where that is, it's somewhere. And go down this list and say for our digitizer, it is the value of our digitizer. And we're bringing these up from disk. Now, I didn't actually go and make the classes that exist for this purpose, but this is concrete versions of the class defined at runtime that we're going to disk and pulling in. And we're casting to, this is generic instrument. Hey, all of these are measurement instruments or actuation instruments. They're some sort of instrument. And then, this is our test bench class that we talked about earlier. We bring it into that function that we briefly looked at earlier, pipe in all of our instruments, and cast them to the appropriate type because we've said, hey, you need to put them in this order. And you can do, any type of management of that, making sure that they're coming in the correct order, or however you want to manage that. But now, we've brought our instruments, which were abstractions and still are in code, into, hey, these are the actual things that we're using during this run of the software. And that's the power of hardware abstraction layer. Now, the person who codes it as if, hey, I am talking to power supply, and I want the power supply to, where are our classes here? Instruments, there we are. I want my power supply to set whether or not I'm current limiting or voltage limiting. I want to set my current limit, and I want to set my voltage limit. And I want to be able to prompt it, hey, can I measure this power supply? If I can, I want to be able to measure with the power supply. If I can't, well, then I won't measure with the power supply because I know that I can't, because I'm forcing you to say, can I measure with this or not? We go into this class's properties. I did this wrong. I should have gone over the Files tab and go to the properties from there. It loads in an instant. If I go to Item Settings, the can measure current or voltage is a required to send classes to override this dynamic dispatch BI. So anything that inherits from this has to say, yes, I can measure, no, I cannot measure. But no. As I was saying, opening from here takes no time, usually. There we go. But our measure current does not have that checked, and our measure voltage does not have that checked. So if we can't measure, there's no reason to force them to say, hey, this is an error. Just don't make them override that. But the power supply is doing the things that a power supply can do and a power supply must do. So any power supply should be able to current limit or voltage limit. Okay, maybe not everyone, but you should be able to at least say, hey, I'm doing this. You should at very least be able to set voltage output, or if it's current supply to the current output. if it behaves like a power supply, you should be able to do things that a power supply can do. This one, or some of these may also behave like a multimeter in some ways, where we can measure stuff, but we don't want to have it be both a power supply and a multimeter, because not all power supplies can do the multimeter thing, and definitely not all multimeters can do the power supply thing. So the way you get around that is the, hey, can I do this thing before you actually do the thing? And likewise, a DMM is able to measure voltage, measure current, measure resistance. XY table is able to go to XY position. You know, these abstract instruments are described in the most generic possible terms that you can do that in and still have a functional program. And then your concrete actually talks to the instrument. Any questions? Because this is the thing that I wanted to talk about most today, hardware abstraction layers. Questions?
So you have one power supply that is just a standard power supply, and another one that is like a triple output power supply. How would you abstract that so that you can use them interchangeably?
The question is, if you have a single output steady rail, you can't control it power supply, versus a 3 output, you can control everything about it, how do you abstract those differently? You wouldn't abstract them differently. If the one can be used for your program, then you have to, with the concrete class of the other one, make it behave like the first one. I don't know if you were here for the last session, but one of the slides said that the input for a child class cannot be more stringent than of the parent class, and the output cannot be less stringent. Likewise, when you're designing the system for this first thing, you have defined your inputs to that class. And then when you go over to the more generically available one, if you want to use that as a descendant of the same power supply, it has to do exactly the same things. If you want to use it as a descendant of a different power supply, now you have more ability, and you can then make both descendants of this new class, both the old power supply and the new, the old abstraction and then new actual physical thing, descendants of the new abstraction. And if you're using the new abstraction and it calls the old abstraction, you have to write your errors in saying, hey, you asked me to do a thing I can't do. Does that make sense? Okay. Anyone else? Anyone have anything they want to say about that particular example? Because I know that I'm not perfect on this and I may have gotten that wrong. We good? Understanding hardware abstraction layers at least a little bit. All right, question?
What is that, adding the extra layers in there, what does that do for timing and things?
What does adding another level of abstraction in do for timing?
Yeah.
I believe that determining inheritance and which child is actually going to be on the line doesn't have too big of a timing hit on the scale of, you know, you're waiting a couple seconds for your power supply to respond. But if you are, you know, in the millisecond range, maybe it has an impact, and you would have to look at that yourself. Were you adding to this?
Similar question continuing to troubleshooting.
Troubleshooting.
Yeah, like if you have an inheritance instrument, I think timing will probably less of a problem. I inherited some code at some point, and it was hard to troubleshoot. So maybe that was just not implemented well, but Have you, because I mean, error propagation from child to parent classes and things like that, have you encountered issues like that?
How do you propagate errors correctly from child to parent? Is that the question?
That is definitely one of, yes.
Okay. Usually your parent, if you have a child on the wire, your parent's never going to see the error. It's going to be handled either by your main program or by another class that you have defined as that child. Because this is an abstract parent. Every single function that this parent uses in the code should be overwritten by a child. It's probably not answering your question.
I think for the most part, I mean, so you're basically saying that error propagation, as long as it's handled correctly in the child object or class, it will not, shouldn't be a problem. It should pop all the way up to where your where you can handle the error.
That's the way that I've always seen it. Question on this?
So in the case he's talking about was an abstract parent class. There is no code for a parent method, so it's nothing to do with the error. So you either handle the error down below at the child level where it understands what those errors in that particular device are, or you pass it to whatever error handling system you have and let that take care of it.
So from the LabVIEW perspective, the abstract class would just have would just still have error, like the.
You still have error lines, yes.
It's the same connector thing.
Just passing through the error and holding that in there.
So in my example, set constant current, constant voltage function, this is the abstract parent of the power supply, the function of that power supply. Yeah, your error line goes through, but it doesn't do anything. Actually, honestly, I should have thrown an error. So if you call the parent class and there's nothing on the line, you're going to get errors saying, I don't know what you're talking about. And honestly, that is the proper way to do abstract classes. Throw an error if you ever find that you are executing an abstract class. All right. I don't know. I have a couple minutes. A minute. I have a minute. Any last questions? This is pretty much the end of it. I've been answering questions along the way. So, with how main code is written to the function of the hardware. Sorry, question.
Yeah, question about the abstraction layer there.
Yeah.
Did you, when you did a dynamic link to the particular class that you finished trying to do, does it use the GUI thread, the GUI thread?
When you do the link,
Yeah, when you do the dynamic link, because I assume you're linking to a library or that it physically is located.
so it's going to do a lookup. It's going to do a file search,
File search, right?
and then it's going to load that class into memory.
And that uses the LabVIEW GUI thread, I believe, right? Is that correct?
I honestly don't know. Any other CL?
It's based on where, I mean, the thread that it uses is based on how you have settings. So if it's being called by a VI in the UI thread, you have to use it. If you have a different thread, force it in a different thread, that's what it is.
Well, the reason I'm asking is in other code and not local code, when you do dynamic link to like to dynamically call a VI in cat library, so it's not with cat library, that uses the GUI thread the first time you call it. Unless you only pull on your reference. So I was wondering.
As you saw, when I was running the factory pattern, it was doing a search,
Yeah.
like your standard I'm launching LabVIEW search for all of your files. I don't know if that uses the GUI thread. I may need to look into that. But yeah, that can cause major issues if it locks your UI or your GUI thread and something happens and now you've hard locked your software. Yeah, it's a concern. Another way that I have dealt with the factory pattern in a configuration controlled environment is just hard-coded the class objects into a case structure, and I have a string coming into that case structure selector, and based off of that string, I launch the specific classes. That way, you have built your classes into your executable. It creates that hard, I know that this class is in here, and so I'm going to encompass it in my build. For configuration control, that was a very important thing, because having stuff floating around on disk that people could change willy-nilly and then our tests would run differently, that did not work. But yeah, I honestly don't know about the GUI thread portion of that question. I apologize. Gotten a little bit off track. I think my time is officially done. But any last questions, comments? No? All right. I don't remember who's in here next, but am I correct in thinking on that?
Thank you.